Hello, Brad Warner here. Wanted to discuss confusion matrices with you. The term confusion matrix comes from statistics and information science, data science, machine learning certainly uses it. There's a lot of different fields who use confusion matrices, but we're going to focus on using confusion matrices for classification problems as performance metrics with machine learning models. So if you have AI, ML components within your applications, within your software, you could leverage performance metrics such as this if, again, you have a classification kind of problem rather than the regression problem. I'm going to show a few little things about using the scikit-learn library in Python to do a little bit of calculations and then a little bit of visual rendering with matplotlib to do some plotting. And this could be used to evaluate my machine learning models and the performance. So here's an example that I grabbed from W3 Schools. They have a lot of references for languages like Python and libraries for like calculating a confusion matrix here within their machine learning category. Went down to confusion matrix here, and they have a little code snippet using NumPy. They calculate some random numbers. Why do they calculate these random numbers? Because they want actual values that you have as your real data that you know as ground truth. And then if you're running a machine learning model, you would get predictions relative to the same inputs that you already know the answers for. So we have the actual values, and then we have the predicted values. We want to compare them and assess and measure how good our predictions were. So if I toss a fair coin or roll a die or scramble a confusion matrix. Oh, sorry, whatever this cube thing is called. If I do some random trials, then can I predict what those are? Like flip heads and tails of a coin? Well, maybe I'll guess right occasionally, maybe not. How does your uh, your machine learning model do? So I copied that example, ran through this, got a little confusion matrix here. Now, I have a few other little code snippets here where I then took that and ran this with a couple different values for the display labels. Notice, because I wanted to use the false and true values instead of 0 and 1 for display labels here for the true axis and the predicted axis, then I saved that with a file name of ft instead of 0, 1. So let me show you that. So it looks like this, same kind of thing, but it has specifically false and true for what we call the true or actual label there. On the other axis here, we've predicted, and that's false and true here. However, and I have this in my notes over here, this could be confusing. So I'm just said here it can be more clear if we use the words negative and positive. So when you're using your own calculations, statistical methods, algorithms, machine learning models, artificial intelligence services, you're going to have a situation where you have, if it's a classification problem, binary classification, you're going to have where the thing is not true. So you could say it's false. However, if we use the word negative, then when we talk about assessing the model as far as whether the prediction matched the actual reality, then we can say whether that's true. And it could be a true negative. We could have an actual value which is positive though, and like have a spam detector or a fraud detector or an illness detector. Some doctors, nurses, medical people have run a scan and checked if someone has some kind of illness, and we can say, oh, it's negative. That means they don't have the illness. The positive thing, this sounds weird, but the positive thing could be that we have spam, we have fraud, we have an illness. Oh no, we don't want any of those really. So sometimes truth is negative, sometimes truth is positive, sometimes the sense of this gets a little bit confusing. But positive simply means that we've detected what we were trying to detect. Doesn't mean it's a good thing in real life. It means we've detected what we were trying to detect as a classification. So if the actual outcome was positive and we predicted it as positive, then we call that a true positive. So the word truth and false, or true and false, are used as the assessment of whether we guessed correctly. The negative and the positive are either for the reality or for the prediction. So if we use those labels, let me show you an example of that over here. Just run this again here with the negative and positive there as the labels. And here I changed one more thing when I ran this a little while ago. I changed my my color map. So instead of being the kind of indigo, purple, yellow theme here, for this negative positive one, I went with the blue and red and green. Just thought it would be a fun scheme. And also there's a poem, a song that is in another video that goes over this. So we have in this kind of rendering of things right here, these kind of four quadrants where up here there's the stuff that we have as actual, really negative value, but was predicted as negative. That's what we would actually call a true negative. Over here, in the next little quadrant, we could say, since it's only a binary classification, it's a 2x2 grid here, we have things that are in reality are negative, but we had classified them here as positive. So they're false positives. We predicted them as positive, but in reality, they're negative. So those are the false positives right there. All right. So keep that in mind. Now, I mean, this quadrant down here is going to be things that are actually positive, but we predicted them as negative. So like it's, actually spam or fraud or some disease. And we were like, nope, it isn't. We predicted wrong, right? So this is another kind of false thing. But what is it? The false negative. So it's not really negative. It's just our prediction is incorrect. So that's a different kind of error, we could say, than the false positive up in this other corner here. Okay, so this is a false. So this is a false negative here. Well, I leave this little quadrant over here. And what do we have here? Well, things that are actually really, honest to goodnessly, positive. And we predicted them as positive. Well, that's correct. That's good. So that's a true thing. But we predicted it as true, and it's positive. So true positives here. So true negatives, false positives, false negatives, and true positives. Of course, if you flipped the axes so that you had, or the labels, so you had the positive on the left and the negative on the right for the predicted axis, and for the actual true or ground truth axis, the vertical axis there, if you had instead a negative on the top and positive on the bottom, if you flip those, so you had the positive on the top and the negative on the bottom, then where these squares go, which quadrant is which, changes according to how you have oriented your labels. So be very careful when you're reading other people's and your own, actually, or my confusion matrices, because they can get confusing. So always check the axes, which is predicted and which is true, and then which is negative, which is positive, right? And then hopefully it'll be a little less confusing, which is the point of confusion matrices, to help make sense of your results. So some other references here that may be useful, and certainly let me know if you'd like any other kinds of demonstrations, and I hope this was useful for you. Thank you.